Let's look at f of x comma y equals 3x squared y, and we'll find the integral from 0 to 2 of the integral from 1 to 3 of 3x squared y dx dy, and the integral from 1 to 3 of the integral from 0 to 2 of 3x squared y dy dx. You'll notice that both the integral signs changed and these things called differentials, dx and dy, also swapped locations. So comparing, yeah, the integral swapped, the dx and the dy also swapped. So the first one of these, I'm using a smaller font here just so that it fits in a line. We should integrate with respect to x. And so that should be x cubed over 3, so the 3's cancels. Yeah, so x cubed y, x going from 1 to 3. If you do that, skipping the details, yeah, 27 minus 1, so 26, right? 26y, integral of 26y dy from 0 to 2, that'll be 13 y squared, and so let's see, 13 times 2 squared minus 13 times 0 squared ends up being 52. Now the other one, we swap the integral signs, swap the dy dx. Now we should integrate with respect to y first. The inner thing is the y. So we'll have x squared y over a 2, there's still a 3. So 3 over 2 times x squared times y squared, which we need to plug in. These are y values, the 0 and 2. I just kind of ran out of room to write that in. But we should plug in y equals 2, then y equals 0. We end up with integral 1 to 3 of 6x squared dx. And if we integrate 6x squared, we'll have 2x cubed, and we evaluate that at x equals 3 and x equals 1, and we're also going to get 52 again. The fact that both of these double integrals ended up being the same number is an example of Fubini's theorem. So if you have a nice function, so in other words, like let's just go with a continuous function, then when you swap both the integral signs and the dy dx, you're really integrating over the same region. And so the point of this theorem is to say, for a nice function, for a continuous function, the order of integration is not going to matter as long as you're doing this over the same region. Yeah, so integrating first with respect to y and then with respect to x, or first with respect to x, then with respect to y, as long as when you swap the dy dx, you have to swap the two integral signs as well. That's the only way you're integrating over the same region. Okay, there is that Fubini's theorem again. Let's take a look at the following. So let f of x comma y equal x squared plus y squared plus 1. And the region we're looking at has x going from 0 to 3 and y going from 0 to 4. So this is the shape of a rectangle. F is a polynomial in two variables. And because you have a polynomial, this function f is continuous. So Fubini's theorem applies, meaning that if you look at the integral from 0 to 4 of the integral from 0 to 3 of f of x y dx dy, and you look at the integral from 0 to 3 of the integral from 0 to 4 of f of x comma y dy dx, notice the swap, both of the differentials and of the integral signs, then these should both have the same value, and both will equal what is kind of more theoretically written as the double integral over the region. Okay, a little moment ago, you were asked to try computing integral -1 to +6 of integral from 0 to pi over 2 of y times sine of x dx dy. The point here being that y times sine of x is continuous, and so using Fubini's theorem, we can actually swap the integral signs, swap the dy and dx as well, and now we could do the inner integral, which is with respect to y, so treat y like a variable, treat x like a constant. And you should get the same number by doing this. This should work out just about as nice as the one that you were asked to do earlier. You should get the same number, and here's the thing, we will revisit this a third way a little bit later.